Okay, so we're going to be talking about constant rate of change for today. So basically, looking into functions, there's an idea of whether, so we talked about whether something is a function or not a function. Remember, if it is a function, then it means that each one of the domains has exactly one range. And it also means that if it's a graph, it has to pass that vertical line test, right? So what we're going to talk about today are functions that are linear. So the idea of linear, what do you think of when you think of the word linear? What comes to mind? You hear the word linear or just looking at the word linear. What word do you see inside of it, guys? Line. And what is a line? It's just a straight path, right? Okay. So the idea of a line or a linear relationship is that you're talking about a straight path, or as you guys would like to call it, a straight line, though a line by definition is straight. I know that sometimes you guys have a hard time with that when you're told to get in line, but it is a straight path. Okay, so linear relationships must be straight. Okay, it could be at a diagonal, it could be horizontal. Can a linear function be vertical? No. Linear function cannot be vertical because remember, if it's vertical, will this pass the vertical line test? No. Remember, the vertical line test states that if you are going to draw a vertical line, it should only pass over the function at one given point. If I draw a vertical line here, I'm going to pass over it at every point. That means that it is not considered to be a function. Okay, it is linear, but it's not a function. Okay, linear functions mean that they are straight paths that are not at an exact vertical relationship. Now, you can have vertical lines, but again, it would not be a function. Okay, so linear relationship, straight lines. Now, in order for it to have a linear relationship, it has to have what's called a constant rate of change. Now, constant rate of change is that value that shows how much is the relationship changing over y versus how much it's changing for x. And it's written in a fraction form. You're also going to know this as a new term called slope. We'll talk more about that next week. But the constant rate of change, for all intents and purposes, we're just going to go ahead and label this ROC, just so that we don't have to keep writing out rate of change. So constant rate of change. The constant rate of change is going to be your change in your y over the change that's in your x. And notice it has that term constant. So let me go ahead and underline those terms, constant. If you are consistently changing by a value of y, but you don't have any consistency for your change of x, then there is no constant rate of change. And vice versa. If there's no constant change in your y, but there is a constant change in your x, there is no rate of change or constant rate of change because it would not be proportional. So we're going to talk about what that looks like in just a second. But in order for there to be a linear relationship, a constant rate of change, also known as slope, so we'll even put that in there, that AKA, it's known as slope, AKA slope. You'll learn more about that next week. You have to have a constant rate of change or a slope in order for there to be a linear relationship. Now, it's also important to understand that before we start, let's talk about how we read tables and how we read graphs. Because you have to know your positionings of your x's and your y's on a table, and you have to understand that when you read a graph, it has to go in a certain direction. So first thing I want to make sure you understand is that if you're talking about tables, there's two ways that a table can be formatted. You could have a vertical table, and when you have a vertical table, your x values typically are going to be on the left side, and your y values are typically going to be on the right side. A vertical table tends to have x on the left and y on the right. Sometimes that might be different, but for the majority of the time, this is the format that it's going to be in. If it's a horizontal table, for the most part, X is typically written on the top and Y is typically written on the bottom. Another thing to take note of, time, measurements of time is always X. If you're ever given a relationship in which they are describing changes in time, whether it's weeks, hours, months, days, minutes, any kind of change in relationship to time, that's going to be your X value. When they're talking about money or even distance, those are typically going to be your Y values. Money or distance, those tend to be our Y values. So if you're given information and it's not displayed in a table or it's not displayed in a graph, if they're just telling you, hey, at 2 hours, they traveled 100 miles. At 4 hours, they traveled 200 miles. You know that the hours would represent the X values and that the distance would represent the Y values. Sometimes you're given word problems and it's not displayed in a table or a graph. You need to know how to distinguish which ones are your X's and which ones are your Y's. Okay? All right, so this is typically what they look like if they're in a table format. Now, reading a graph. When we read a graph, it's just like reading a book. When you read a book, you start where? If you're looking at a page, do I start in the center? Do I start all the way at the bottom? Do I start at the top? Do I start at the top right? No. Where do I start? Top left. So that's important. Now, sometimes it might not be always at the top. With a graph, it's just important to understand that you read a graph from left to right. When you're reading a graph, you start at the leftmost point, whatever point is all the way to the left of the graph, and you work your way to the right of the graph. Sometimes that point might be up at the top and you're going to read the graph and it works its way down to the bottom right, just like when you read a page. Sometimes the point that's all the way to the left might be at the very bottom and then you're working your way up to the top right. Okay, those will describe the correlation or the type of slope or the type of rate of change. Okay, if it starts at the top left and works its way down to the bottom right, that has a negative association. If it starts at the bottom left and works its way to the top right, it has a positive association. And again, you'll see that when we work out our constant rate of change and when we get into slope next week. Okay? All right, so let's take a look here at these examples that we've got on our page. Example number 1, we're identifying the relationship and we're identifying it as if it was linear or nonlinear. Now, if it is a linear relationship, we're going to state what the rate of change is. Because again, if it's linear, it has to have a rate of change. So looking at this very first problem, I have hours and I have money. How much hours and how much I'm being charged. Remember, we stated that the X is always going to be an hours or time relationship, which happens to be on the left side of the graph. Money is going to be that Y relationship, which happens to be on the right side of our graph. So this is our vertical table. In order to identify if it is a linear relationship, I have to see if it has a rate of change. So like I said, we're going to just go ahead and label it ROC. And that rate of change has to be set up as a change over the Y, or change of the Y's, over the change that exists in your X's. So let's start with the Y's. When I mean change, I mean as we're going from one Y value to the next Y value to the next to the next. So let's take a look here. We're going from $10 to $18. The first thing that I need to note is that an increase or a decrease? Am I increasing or decreasing? Increasing. So I'm going to go ahead and put a plus sign because that means that I'm increasing. And how much am I increasing by? 8. Good. Okay, now I'm going from $18 to $26. That is also still an increase. And what is it increasing by? 8. And then from 26 to 34, that is an increase of 8. Okay, so notice, remember before I said it has to have a constant change in y. Is this consistent? Yeah, they're all the same value of change. That's a good thing. So we're going to go ahead and put down that this is a positive 8 at the top of my fraction. Now we're going to do the exact same thing for the x's. We're going to identify the change that occurs for our x values. Going from a 1 to a 2, what is that? A plus 1. Good. So I'm going to put a plus 1. Going from 2 to 3, what is that? Plus 1. From 3 to 4, plus 1. Okay, so we are having a constant change in our x. We are constantly increasing by 1. And then 8 over 1 can just be simplified to 8. So our rate of change is equal to 8. This represents $8 per hour. You always want to relate it back to what it's representing. It's $8, right? $8 per 1 hour. $8 per 1 hour. That's our rate of change. And since it has a rate of change, is it linear? Yes. So we are going to put down that it is a linear relationship. So we have two answers, what the rate of change is and the fact that it is a linear relationship. Okay, when we're looking at a graph, we're going to do the exact same thing, but with a graph to identify the rate of change, you're looking again at point to point. So I'm going to go ahead and darken these points a little bit more so that you guys can see them easier from your seats, even though you do have it in front of you. But here are my points. And now it's really important. Every year, I have students try to read a graph, but they're not reading it correctly. And I'll show you what I mean. When we're going from y to y, so if I'm wanting to go from one point to the next point, my y-axis, does it run up and down or left and right? My y-axis, up and down. So that means I'm looking from this point, I want to get down to the level of the next point. So I'm just going to draw a vertical line down. I'm trying to identify what this change represents. Who can tell me what this change is going to represent? First of all, are we increasing or decreasing? Decreasing, so I should put a negative, right? A minus sign. And what am I decreasing by? By 20. Good. Every year I have kids tell me they're decreasing by 2. Why do you think they say that they're decreasing by 2? What makes them decide that it's a decrease of 2? What do you think? Jair? Huh? They're just counting the boxes, right? They're counting the 2 spaces that they're decreasing by instead of looking at the axis. See, the axis is telling us what each of these lines represents. And each box represents a change of 10, right? If we're looking here, we're going from 80. If we go to the next line, that would be 70. And then this line, that's 60. So we've gone down a total of 20 units. 20 units, okay? So here, a decrease of 20 units is what's happening, not 2. Now, if I go ahead and look at this next one, it's also the same, a decrease of 20 units. So I'm going to put negative 20 here as well. So our rate of change is going to be the negative 20. Now for the for the x, Again, you got to make sure you're reading the graph very carefully. For the x, what is our change going to be here? So, but what is it? We're going from this point to this point. It's increasing by what? 8. So I'm going to put a plus 8. Plus 8. Okay, so we have a positive 8. So notice we've got a negative over a positive. I'm going to go ahead and simplify this. They both happen to be divisible by 4. That's going to give me a negative 5 over 2. Negative 5 over 2. Or you could say negative 2.5. For now on, you are no longer going to change your fractions into mixed numbers. Your fractions are going to stay either improper, or sometimes they might even convert them to decimals. But you will no longer change any of your fractions to mixed numbers. The reason for that is because when we're talking about slope is a value of fraction that's rise over run. So it has to be just a fraction, whether it's proper or improper. You leave them in this format, no more mixed numbers. Okay? Everybody clear about that? All right, so we do have a rate of change. That means that this is going to be a linear relationship. Our rate of change is negative 5 over 2 or negative 2.5. It is linear. I want you guys to go ahead and try problem C on your own. Try problem C on your own. All right, so let's take a look at this one. Can somebody tell me, is it linear or a nonlinear relationship? Raise your hand, tell me. Nobody? Bonnie? Nonlinear. Why is it nonlinear? Because the y doesn't have a constant change in relation to the constant change for the x, okay? So here, if we're taking a look, the change that's occurring in these y's, it's decreasing each time, but the first one decreases by 5, while the rest of the time it's decreasing by 4. Okay, and so that's not constant, which is okay. It's okay for it to not be consistent as long as the x also follows a proportional non-consistency. But when we look at the x is increasing by 5 every single time. So x has consistency, whereas the y does not have consistency. That means it cannot be a linear relationship. There is no rate of change. Therefore, that means it is nonlinear. It is a nonlinear relationship because of the fact that there is no rate of change. Negative 5 over positive 5 is not the same thing as negative 4 over positive 5. Now, like I said, it's okay for there to not be consistency on the y as long as there's also a proportional non-consistency on the x. They have to have proportional relationships. So what we're going to do is in this little spot, I'm going to show you a couple of graphs that are, or tables, sorry, a couple of tables that are considered to be linear relationships, but they're not showing consistency, but they do show proportionality for it. So let me go ahead and give you an example. Write this down in this little spot. If we have an x and a y relationship, so we'll call this table D. Table D. We have x and y. All right, so we have x, y. We have 0 and 2, 2, 8, 3, 11. We'll say 6 and 20. Okay, so having this, if I'm going to check the change that's occurring in the y, the first change that happens to go from 2 to an 8, that's an increase of 6. But then when I go from 8 to 11, I'm only increasing by 3. And when I go from 11 to 20, I'm increasing by 9. So there's absolutely no consistency here, is there? But again, like I said, this is a linear relationship because I'll show you why. When I go from 0 to 2 for the x's, that's an increase of 2. When I go from 2 to 3, that's an increase of 1. When I go from 3 to 6, that's an increase of 3. There's no consistency here for the x's either. So what I must do is I must check to see if each of these represents the same rate of change, meaning it simplifies or is equivalent to each other. Okay, so when I'm looking at it, I can set this up as 6 over 2, 3 over 1, and 9 over 3. All of these values are equal to each other because of the fact that they all equal 3 over 1. They all simplify to 3 over 1 or just 3. So that means that this is considered to be a linear relationship. They all simplify to the exact same equivalent ratio. So that makes this a linear relationship. I want you to try one on your own. So on this little side, we're going to do another example, example E, that you'll write in. Here, let me zoom in so you can see it easier. All right, so we've got 17 and 47, 9 and 23, 4 and 8, 1 and negative 1. Okay, so I'm already telling you this is a linear relationship. So I want you to find out why it's a linear relationship. Find out what the rate of change is going to be. All right, who can tell me what the rate of change is going to be for this one? Alonzo? 3 over 1, right? And it's positive. Even though we're noticing that it's decreasing, the fact that it's decreasing on both ends, a negative over a negative would come out to being a positive relationship. So we're going from 47 to 23. That's going to be a decrease of 24. We're then going from 23 to 8. That's a decrease of 15. And then we're going from 8 to a negative 1. That's a decrease of 9. And then for our x's, going from 17 to 9, that's a decrease of 8. To go from 9 to 4, that's a decrease of 5. And 4 to the 1 is a decrease of 3. So again, there isn't much consistency on both ends. However, when we look at them in a format of equivalence, when we set it up as negative 24 over negative 8, and we set it up as negative 15 over negative 5, and we set it up as negative 9 over negative 3, each one of these is equivalent to each other. They all equal 3 over 1, a positive 3 over 1. So that, again, makes it a linear relationship because it has that rate of change. Are there any questions so far? Okay, so let's go on to proportional relationships. So proportional relationships also means it's going to be linear. If it is proportional, it has to be linear because by definition, proportional relationships are straight lines, but they also have to have a proportionality to them. And in order for them to have a proportionality, they have to pass through the origin. Who knows what I mean by origin? If I say the origin, what point on our graph represents the origin, guys? 0, 0. Not just 0. Remember, a coordinate has two values in it, an x and a y. It's 0, 0. Okay, so the origin means 0, 0. So in order for this to be a proportional relationship, in order for it to be a proportional relationship, not only must it be a straight path, so we'll put off to the side straight line, and passes through the origin, which is at 0, 0. Okay? So in order for there to be a proportional linear relationship, it has to be a straight line and it has to pass through the origin. So that means you're going to have a starting point at 0, 0. And then for the rest or the remainder of your graph, you're going to have a constant rate of change. Okay? So taking a look here, we've got our table. This is our x values, the time. The speed that we're moving at is going to represent our y values. We started at 0, 0, so that's important. It starts at 0, 0. Now we need to check to see, is it going to create a straight line by having a constant rate of change? So let's take a look at our x's. When we're going from one point to the next, from 0 to 1, we're increasing by 1. When we're going from 1 to 2, we're increasing by 1. From 2 to 3, it's an increase by 1. From 3 to 4, it's an increase by 1. From 4 to 5, it's an increase by 1. So our change in our x is consistently increasing by 1. The change in the y is consistently increasing by 9.8. So every one of these is an increase of 9.8. So that means that our rate of change is going to be 9.8 over 1. 9.8 over 1, which means that its speed increases by 9.8 meters every second. Okay, so this is proportional. It is a proportional relationship because it has a rate of change. Okay, it has a rate of change, and it starts at the origin, 0, 0. So it is going to be a proportional relationship here. It is proportional because it's got that rate of change, which means it's straight. It is linear. And it's going to pass through 0, 0 or start at 0, 0. So now what we want to do is we want to go ahead and graph it. Now, when you're creating your graph, notice that nothing is posted on here. Sometimes when you're creating your graph, you have to create the axes. And that means you have to think, what are you going to count by in order to make sure that you are able to display all of your data. So my largest point goes up to 49. Now, it happens to be that I've got 14 units here, 14 squares here that I can count by. So I want to make sure that when I'm counting by a constant interval, remember, we don't want to change the interval that we count by. That makes it misleading. If I go, oh, I'm going to count by 2s, and then I'm going to count by 10s, and then I'm going to count by 1s, and changing the interval count, that makes it misleading. That goes all the way back to first semester's inference unit. So when we're talking about choosing an interval, we got to be consistent with what we're going to count by. Because I need to make sure that I get up to at least 49, the best value that I can count by, since I only have 14 boxes to count with, is to count by 4s. That will fully cover everything. Because what's 14 times 4, guys? What's 14 times 4? 56. If I counted by 3, 14 times 3, that's only going to get to 42. So that's not going to cover enough. So counting by 3s, not enough. Counting by 4s, just over the mark. So each one of these boxes, again, we're going to start at 0 down here at the corner. And I'm going to zoom into here so you can see it easier. obviously want to start at the origin. And each one of these boxes, I'm going to count by 4. So I have 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48, 52, and 56. Okay, so that's going to cover enough distance for my y. Now, my x is a little bit different, isn't it? My x values, I'm ranging from 0 to 5. I've got plenty of space to be able to do that. So in fact, what I'm going to go ahead and do is I'm just going to go ahead and skip every other line and count by ones. So that means each of these boxes would represent a half. So that would be a half. Go to the second line, that's going to be a 1. Skip, go to the fourth line, that's going to be my 2. Skip, go to the next one, that's going to be a 3. Skip, go to the next one, that'll be 4. Skip, go to the next one, that'll be 5. Skip, go to the next 6. Skip, go to the next and 7. Okay, so that way I have plenty of space to be able to display it. Now, when I'm graphing these, it's important to note that I do have a bunch of decimal values, and that's really, really hard to be able to be accurate with when you're graphing. So the best thing to do is to give an estimated location. So let's start with the first one. We're going to start with, and I'm going to go ahead and use my pink. Or maybe I might use my, I want to use orange. Yeah, we'll use orange. Orange will stand out nicely. Okay, so obviously we're going to start at 0, 0. We're going to start at 0, 0 because that's what the graph is starting at. Then we're going to go over to 1 for my x and go up roughly to where 9.8 is. 9.8, that's very close to 10. And 10 is roughly halfway, or is almost halfway between 8 and 12. That 9.8 is going to be almost halfway between the 8 and the 12. So when I'm marking it, I'm going to just basically make a dot in between. I'm going to go ahead and zoom in now to the graph so that way it's easier for you guys to see that because you've got the table in front of you to look. Okay, the next point that I want to do is at 2 and then 19.6. So I'm going to go over to the 2 and 19.6. Again, that's almost 20. So I'm going to make it just right at the 20 mark, maybe slightly below it. At 3, it's at 29.4. 29.4, that's just a little bit less than halfway, right? That's about a quarter of the way up between 28 and 32. At 4 seconds, it's at 39.2. So we're going to go up to roughly pretty close to the 40, about a quarter of the way between 36 and 40. And then at 5 units, it's at 49. 49 is just about a quarter of the way between 48 and 52. And then there's our relationship graphed. Now, it's important to know that this being the linear relationship, to check it, it should form that straight line. When you're trying to connect your straight lines, do you want to do it freehand? No. You want to make sure you've got a straight edge. So a ruler is a great thing to have. If you don't have a ruler, you can always use a book, something that's straight. In fact, if you've ever gone on to my old videos 2 years ago, I used Post-it notes to connect them. So you can use anything that is a straight edge. You just wanting to make sure that connects and forms that nice, lovely linear relationship. And again, because we aren't able to get exactly where it needs to be because it does have decimal values, you might be a little bit off, but just the idea of knowing it's supposed to be linear because it does have that constant rate of change. As long as it's very, very close to each other on the lines, you're good. All right, if you go to the next 2 slides, you are going to go ahead and do those problems on your own. And then we'll check them in about 5 minutes. All right, let's go ahead and go over each of these. So this is talking about the hours that you spend studying compared to the test score that you might receive. that if you only spend 1 hour studying, it might be a 52. Those who spent 2 hours studying got the 68. 3 hours studying was an 84. 4 hours studying is a 100. So remember, hours is going to represent the x values. And so our x here in this table is consistently increasing by 1. And the score that is achieved is the y values. This is consistently increasing by 16. This is actually not a realistic representation of what actually happens, because we do know that in real life, sometimes you might study a lot and still not score very well, and that there are some people who don't study and score pretty high. But this is just, again, trying to show you a relationship. There is a rate of change, a constant rate of change that exists here. Since we are consistently increasing by 16 points on the test over 1 hour studied, that means our rate of change is going to be 16. Okay, so that does mean we do have a linear relationship. Now we have to identify if that linear relationship is going to pass through 0, 0 in order to make it proportional. So we're going to go ahead and graph it. Again, because my hours is only going from 1 to 4, I'm just going to go ahead and skip by every other. If you didn't do that, that's perfectly fine. I'm just doing it for mine. And since I need to get up to a 100, the best thing that I can go ahead and count by is going to be 8. 8 would be the most logical sense here. So I'm going to go ahead and count by 8. So it's 8, 16, 24, 32, 40, 48, 56, 60, 62. Let's see here. No, wait. 64. Oh, dear Lord. 64. Then we've got 72, 80, 88, 96. And then we'll get up past the 100 mark, which would be at 104. Okay, so I can go ahead and stop there. Okay, so when I'm creating my graph, again, I'm going to use orange because it stands out nice and easily. At 1, I'm roughly at 52. And 52 is going to be just about halfway between the 56 and the 48. At 2 hours, I'm at 68, which is about halfway between 64 and 72. At 3, I'm going to be at 84, and that's halfway between 80 and 88. And at 4 hours, I'm up at 100, which is halfway between 96 and 104. So now when I graph those and then connect them to show the linear relationship, is that going to pass through the origin? Yes or no? No. It does not pass through the origin. In fact, where it passes is when x is at 0, it's stating that it's going to be roughly around 36 points. Okay? So this, even though it is linear, it is not proportional. So it's linear, but it's not proportional. And like I said before, not all linear relationships have to be proportional. It can only be proportional if it's crossing through 0, 0. So we do have a linear relationship because it is creating that straight line. It has that rate of change, that constant rate of change, but it's not proportional because it didn't pass through 0, 0. Let's take a look at the next example. Okay, again, here's our x's, the weight in pounds versus our y, which is the mass in kilograms. Okay. So as the weight in pounds is increasing, it's increasing by 20 every single time. Increasing by 20 every single time. The mass here is also increasing. It is increasing by 9 consistently. So the rate of change is going to be 9 kilograms over 20. And that cannot be simplified. That's as simplified as it's going to get. 9 over 20 is going to be the linear relationship. So it is linear. We can go ahead and check that off. Now we need to see, is it going to pass through the origin? So again, because my x has to get up to a value of 80 or past that value of 80, I'm just going to go ahead and count by tens. So I'll do 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and I'll go a little bit past it, 110 and 120, and I can stop there. Because my y's need to get up to 36, I can go ahead and count by threes and easily get into 36 there. So I'm going to go 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, and 42. So I can easily count up to 36 and be able to incorporate it. All right, now I just have to plot the points. When x is at 20, y is at 9. So I'm going to plot it right here. And that's nice because it plots directly on the units. At 40, we're at 18. At 60, we're at 27. At 80, we're at 36. Okay, now I'm going to go ahead and connect them. When I connect it, does it pass through the origin? Yes or no? Yes, it is going to connect here at the origin. Even though the origin is not displayed in the graph, it is going to pass through the origin. So that means that it is a proportional relationship. It passes through the origin or through 0, 0. So it is going to be proportional. So remember, it can only be proportional if it is linear and passes through the origin. Tomorrow, we're going to do some station activities. So I'm going to be splitting you guys up into random groups. And we'll do several different stations rotating amongst them. Some of it's going to be things like IXL. Some of them are going to be puzzles that you'll be doing. But we'll be rotating throughout them in order to practice this portion. Go ahead and pack up.